Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Capillary Viscometers. The question is that how do we know that a given fluid is Newtonian or non-Newtonian? If it is non-Newtonian, what kind of non-Newtonian it is? That we should know, right? If we should know that information, so what information should we have about the fluid? We should have information about the so-called shear stress versus shear rate, and then normal stress differences versus shear rate. This information we should have, right. So, that means with respect to the shear rate, how the shear stress and normal stresses are varying, that information we should have for a material. So, for a given shear rate, that means the material, whatever the fluid for which we wanted to measure the rheology, we should allow that material to undergo some kind of deformation. When it is undergoing deformation, then only we have a deformation rate, then only corresponding shear stress or normal stress would be there, or both shear stress and normal stress would also be there depending on the nature of the fluid. So, but that means that means what? We have to have a kind of a rheology measuring device or system such a way that we should allow that material to undergo certain kind of deformation, right. So, now when we talk about deformation, any geometry, whether you take flow through pipes, any geometry like flow through pipes you take, or you take a concentric cylinder geometry, right. The material, if it is undergoing some kind of flow, so there would be deformation, that is what we understand, right. So, now when the material is having are allowed to flow through certain geometry, right. So, then what happens, we understand that there would be a kind of a relation pressure drop versus volumetric flow rate in general, if the flow is because of the pressure drop. So, such kind of information we have. We also know that the velocity, whatever the velocity of the fluid is there within the system, that within the system whatever the fluid is flowing, so because of that flow the velocity of the fluid elements varies from point to point. That is what we understand for any geometry that we take, right. So, when the flow and when the velocity is changing, there would be a kind of a change in velocity. So, then deformation would be there. So, that means deformation or shear rate, rate of deformation or shear rate is also changing from point to point. So, then accordingly corresponding shear stress and or normal stresses would also be changing, isn't it. So, that means we are not having one single value of shear stress or shear rate or normal stress for a given one single value of delta p. Let us say you are taking the flow, you are allowing the flow to take place because of some pressure difference, right. Because of that pressure difference you are making the flow to occur, but let us say if you maintain certain pressure drop and then flow is taking place. So, then within this flow geometry at each and every location the velocity component, all the velocity components would be having different values, right. So, now correspondingly at each and every location within the flow domain, the shear rate and then shear stress and then normal stress differences would also be different, obviously. So, now which value should we take, because your pressure drop is only one single value for given one particular situation. For other situation or other velocity you change again one some other pressure difference like delta P2 or delta P3, something like that, that is a different thing. But if you are maintaining certain pressure difference, so then you are having one kind of one flow which is having certain average velocity or volumetric flow rate, whatever. But within the system you are having different velocity at each and every locations. If you change the location within the system, velocity is changing, so shear rate is changing. So, the shear stress and normal stress would also be changing, right. So, now which one should we consider? So, that is the question. We cannot consider these values at all locations. So, we should have a kind of device or rheology measuring system such a way that the flow domain or the region that is available for the fluid to flow, that should be very narrow. That should be very narrow, so that whatever the changes are there in shear stress or shear rate from one location to the other location, they would be very small, that those changes may be neglected. So, that is the one important thing that we have to observe before going into the different types of rheometers that we are or viscometers that we are going to study in order to measure the rheology of a given fluid, right. So, first thing is that one. Narrow gap or flow region has to be narrow, so that change in shear rate or shear stress or normal stress, whatever is there, that change should be very small from one extreme of the flow domain to the other extreme of the flow domain. Let us say this pipe only if you take. So, if you change R value from 0 to R value capital R value 0 is nothing but center of the pipe, and then R value small r is equals to capital R is nothing but wall of the tube or cylinder wall, circular tube, whatever you have taken. If this difference from 0 to R, this difference is very small, maybe 1 mm or 2 mm, that means it is in terms of meters, it is having 10 power minus 3 meters. So, then obviously the change in shear rate or shear stress from center to the wall is going to be very small, so that can be neglected. That is one point. Second point is that in such kind of studies, whatever geometry you take, experimentally what are you measuring, that is the important. You are not measuring directly shear stress or shear rate directly, isn't it? So, whatever the information tau versus gamma dot or N1 versus gamma dot or N2 versus gamma dot, this information whatever is required for your analysis, that should be having some relation with the measurable quantities, because tau, gamma dot, N1, N2 etc. you are not going to measure directly. Let us say if you have a pipe flow through a pipe. So, then what you can measure? You can measure the volumetric flow rate for a given pressure drop experimentally. That is what you can do. If you are varying the temperature, then for different temperatures you can do these things, right. So, let us forget about the temperature and all that for the time being. So, if you maintain some delta P and then corresponding volumetric flow rate you get, that means V average velocity versus delta P you are getting, that information only you are getting. For this case, let us say pipe flow case I am talking about, right. So, then what is the thing is that you have to have a kind of relation where you can make a connection between this shear rate, shear stress with measurable quantities, something like pressure drop and then volumetric flow rate, etc. So, relating delta PQ to gamma dot, tau, N1, N2 etc. That is the second point. That is, these are the two important things one has to keep in mind before going into details of any type of rheometers or viscometers which are used for measuring the rheology of the fluids, right. So, now we are going to discuss different types of rheometers or viscometers in this and then coming couple of lectures, okay. So, but primary target the geometry, the flow, first we have to have a kind of flow geometry where we can allow the fluid of unknown rheology to undergo certain kind of deformation, right, and then that deformation should be such a way that the change in shear rate or shear stress or normal stress from one location to the other location or one extreme to the other extreme of the flow geometry should be very small. And then the second one is that whichever the geometry you consider, you make certain balance equations and then develop equations so that you can relate these measurable quantities like volumetric flow rate, pressure drop etc. to the shear stress, shear rate etc. Okay. So, these are the two things one has to keep in mind before starting details of a so called rheometry of non-Newtonian fluids. Of course, if the fluid is Newtonian, then also the process is exactly same. Only thing that if it is a Newtonian fluid, the shear stress versus shear rate curve would be straight line passing through the origin having the constant slope mu, viscosity mu, okay. Otherwise the process is same. So, now we will be discussing rheometry for non-Newtonian fluids. Rheology of non-Newtonian fluids is not straightforward obviously, because you do not know what is the nature of non-Newtonian behavior that material is having. Is it shear thinning, shear thickening, or is there any plastic behavior like in viscoplastic material, or is there any elastic behavior like in the kind of viscoelastic material, etc. So, those many complications are there in non-Newtonian fluids. So, then obviously, the rheology of these non-Newtonian fluids is not going to be straightforward. You need to have a proper device to measure the rheometry or the rheology of these non-Newtonian fluids. Further, the complications may even increase for some kind of suspensions where the mechanical properties may be of a nature such as nonlinear, dissipative, dispersive, and thixotropic nature. When the mechanical properties of some concentrated suspensions are having such kind of properties like or nature like nonlinear nature, dispersive, dissipative, and thixotropic nature, then rheological measurements of such kind of non-Newtonian fluids or concentrated suspensions which are non-Newtonian fluids, that becomes even more difficult. So, now before going into the details, one thing wanted to mention. So, most of the non-Newtonian fluids are not single phase materials. Majority of non-Newtonian fluids are a kind of multi-phase particulate systems like emulsions or suspensions, soups, etc. These kind of materials where there are some kind of constituents within the solution that we have taken, right. So, that is what we should realize, that majority of it is not true that for all that all the non-Newtonian fluids are not single phase fluids. So, there are some exemptions may be there, but majority of the non-Newtonian fluids are some kind of suspensions or particulate matters or emulsions like that. Okay. So, now obviously, when you have such kind of constituents within the material, right. So, you need to have a kind of narrow gap flow geometry for rheology measurements as just explained. So, but when you are allowing or pushing through these concentrated suspensions or emulsions to pass through such narrow channels, then what happens? The rupture of particulate systems or emulsions may take place. So, that is the another problem one may have. So, right. So, though it is better if the rheology measuring system provide a constant or nearly constant shear rate, we need to have a kind of a case where the rupture, so called rupture of emulsions, etc. should not take place, because if the emulsions or particulate systems, etc., some breakdown of this of the material is taking place. So, then again it is going to have a kind of change in properties. So, it is obviously better that you have a rheology measuring system that provide constant or nearly constant shear rate. Constant is not possible, but nearly constant shear rate is possible anyway, right. So, but and this constant nearly constant shear rate is possible by using narrow gap shearing geometries such as coaxial cylindrical geometry, cone and plate geometry, etc. But the problem is that these are often of limited utility for characterizing non-Newtonian fluids, because as mentioned, constituents of non-Newtonian fluids, non-Newtonian multiphase systems precludes such narrow gaps, leading to rupture of particulate systems or emulsions, etc. Because of such kind of reasons, so then even the narrow gap shearing geometries, even though theoretically they are good for a reliable measurement of rheology of such materials, because of such kind of problems like rupture of particulate systems or emulsions, etc. These are these narrow gap measuring systems are preclude because of this non-Newtonian multiphase system, they precludes the use of such narrow gaps. Okay. However, need not to worry, when we go into the details, we will be having certain situations wherever there is a inconsistency in measuring of rheological behavior. So, that means inconsistency is there, that means there is some possible source, there is a source of error, and then we can make, so then we have to make adjustment or correction for those sources of error. So, those things anyway we are going to see, but this is the problem, one of the problem of a narrow gap shearing geometries if you are using for measuring the rheology of non-Newtonian fluids. So, but there are several approaches have been developed to overcome such limitations also. So, then we are going to see in detail one after other in coming couple of lectures. So, now we start with capillary viscometers. Okay. So, what is a capillary? Capillary is a straight tube of a very small diameter compared to the length of the tube, right. So, that is large length by diameter ratio tubes, whatever circular tubes are there, those things we can regard as capillaries. That means, if you have a straight pipe whose diameter is 1 mm, but the length is let us say 200 mm or 150 mm. So, then we can say that straight tube of 200 or 150 mm length and then 1 mm diameter, that can be regarded as capillary in general. Okay. Now, these capillary viscometers, what happens in general? We have a container in general, roughly, like we are going to see details later anyway. So, this bottom of this container is having a provision to fix a capillaries of a different diameter. So, this capillary is having, let us say, some diameter d. So, whatever the material whose rheology you wanted to measure, that you pour in the container and then you apply certain force the pressure difference, so that you can get the material flowing out. So, then for delta P versus Q information you can obtain when you are applying certain or when you are maintaining certain pressure drop, the material, that container whatever is there, that will flow through the capillary once you open the opening at the bottom, right. So, you measure this volumetric flow rate with respect to different delta P. That is the simplest way of doing this capillary viscometer, or applying these capillary viscometers for rheological measurements. So, that is crudely that is what a simple capillary viscometer, right. So, then what you see here, it is setup is very simple. You just need a container, you just need a capillary of different diameters. The container should have an opening such a way that varying diameter capillaries can be attached to that one, right. You should have a provision to measure volumetric flow rate, you should have a provision to measure the pressure drop, that is it. So, it is very simple, and then cost also, you does not require much cost for this, and then it is also found to be reliable. Okay. So, these capillary viscometers are commonly used because of their simplicity, low cost and accuracy. And these are similar to many process flows involving pipes, because in general industries we have a situation like through pipes materials are flowing in general, right. So, that is having similar behavior like flow through capillary kind of thing. So, they are having similarity, these capillary viscometers are having similarity to many process flow situations involving pipes. Thus, these are widely used in process engineering applications and often converted or adopted to produce slit or annular flows wherever required, so that inline rheology of that material which is flowing through pipe can be measured without any difficulty. Okay. That is one of the major advantage from the industry point of view. That is the major advantage of capillary viscometer from industrial application point of view. In circular tubes, the shear rate is maximum at wall and 0 at the center, because let us say what we understand from our previous transport phenomena course that we have studied in our UG courses, that if there is a fluid is flowing through a tube, circular tube, what happens under the fully developed flow conditions, the flow rate something like parabolic like this for Newtonian case, for example, right. So, at the center we have the maximum velocity, at the tube wall we have the 0 velocity, right. So, then velocity is changing, it is decreasing from r is equals to 0 to r is equals to capital R is the radius of the tube. So, as we as we move towards the wall from the center, the velocity is decreasing, that means shear rate is increasing. Shear rate is 0 at the center, and then gradually it increases and then it attains a maximum value at the wall. Okay. Now, let us say if the capillary is having diameter, let us say 1 mm, right. So, that means 10 power minus 3 meters. Okay. So, whatever the shear stress that is there, that shear stress would be maximum at the wall and then minimum or 0 at the center. It should be 0 at the center and maximum at the wall. So, that would be how much, if it is your d is changing from 0 to 10 power minus 3 meters or 0 to 1 mm, such a small variation. So, that is not going to affect much in the values of shear rate and shear stress and and shear stress and shear rate and shear stress. So, that is the advantage that we are taking this case anyway here. So, thus restricted for because of these variations, such kind of capillary viscometers are often restricted for steady shear stress versus shear rate measurements for time independent fluids in general. So, time dependent fluids, it may be not reliable to go for a capillary viscometers. Okay. Now, what we do? We try to develop working principles for these capillary viscometers. Developing working principles or equations for this capillary viscometer is nothing but you are going to develop a relation for shear stress in terms of measurable properties, something like pressure drop or volumetric flow rate or average velocity, something like that. Similarly, you are going to develop a relation for the shear rate gamma dot as function of either pressure drop or volumetric flow rate or average velocity, whatever. That is what we are going to do now here. Okay. So, we see what are these relation exactly by development here. So, now consider an infinitely long circular tube which is a capillary of radius r, so that you can have a large length by diameter ratio which is more than 150 or 200, something like that, right. So, let us say if you take the capillary of diameter 1 mm, so the length should be at least 150 mm or higher, minimum 150 mm it should be there. So, that L by D is going to be 150 or higher. Okay. That is what mean by large L by D ratio, length by diameter ratio. Consider a fluid is flowing in this capillary due to pressure difference, that is because of there is some pressure difference is there, because of that one pressure, because of that pressure difference the flow is taking place under the constraints. The flow is taking place because of the pressure drop, but we are taking some constraints into the consideration. What are those considerations? That is the flow is fully developed, steady flow and incompressible fluid. Right. What is the what do you mean by fully developed flow? So, that means in the flow direction, fully developed flow in the flow direction, whatever the let us say flow direction is z direction here, and then there is a velocity is in the z direction is nothing but Vz. So, dou Vz by dou z should be 0, that is what mean by fully developed flow condition. Or pictorially, so you have something like this, a tube like this. So, at the entrance if you draw a velocity profile, let us say you have the uniform velocity you are given initially. So, then it develops something like this, further it develops something like this, and then gradually at certain locations it becomes parabolic like this. So, this parabolic profile for I am talking about Newtonian fluids, it is not going to change even if you increase even if you go higher values of the z. This is z direction, this is r direction. So, this whatever the velocity, that is the velocity component or stress etc. are there. So, they are not going to change in the flow direction, they are not going to change in the flow direction, that is what meant by fully developed flow. So, now within this flow geometry, consider a fluid element and then name it ABCD. The fluid element is having radius r and length L, right, pictorially if you see. So, it is a infinitely long cylinder. So, then what we are doing, we are not drawing in the locations near the entry and then near the exit, but we are taken somewhere in between the location where fully developed flow is established, where the fully developed flow is established and then flow is steady, right. So, now here within this one we have taken a fluid element A, B, C, D, right. The length of the fluid element is L, the radius of this fluid element is small r, the radius of the tube is capital R, pressure at the inlet is P, pressure at the outlet is P plus dP. So, now here in this case we have taken the geometry such a way that only velocity component existing is Vz, or velocity component in the flow direction is dominating, it is very dominating compared to the velocity components in the other directions. So, V theta, Vr are going to be 0 or approximately 0, they are very small compared to the values of Vz, whereas Vz is function of r only. So, now that is what the constraints we are having. We are having only Vz component of velocity which is changing only in the radial direction, that is in the r direction. So, because only Vz is existing and it is function of r, so then only stress that is going to exist here is shear stress tau Rz. Other component of the shear stress would not be there, and then normal stresses we are not considering here in this possible way. Okay? Because we are doing this analysis for a time independent non-Newtonian fluids. So, only velocity component exists is Vz, which is function of r. The same picture is shown here again. The pressure at inlet AB is P, and then pressure at outlet CD is P plus delta P. So, that we can do the balance subsequently. The shear stress along this fluid element is only tau Rz is existing, that we have seen, right. Now, if you make a balance, like whatever the force balance that you do, let us say the force due to this pressure whatever is there or pressure difference, that should be balanced by force whatever is there because of the shearing action. So, that is P multiplied by pi r square is the force at the inlet of this fluid element, because the fluid element is having the radius r. Remember this is a circular tube, we are drawing two dimensional thing, and then this fluid element is also cylindrical. The fluid element is also cylindrical whose radius is r but length is L. So, cross section area of this fluid element is pi r square. The pressure at the outlet is P plus delta P multiplied by the cross section area of the outlet is again pi r square. So, difference if you do difference of these two if you do, that should be balanced by the shearing force. So, shear stress is tau Rz, and then if you multiply by the surface area of the that element, whichever the element, that fluid element ABCD you have taken, so then you get the shearing force. The surface area of that ABCD fluid element is nothing but 2 pi RL. So, now that means if you do the simplification, you will get tau Rz is equals to minus delta P by L R by 2. So, for a given case, when you are maintaining constant pressure drop to get a certain flow rate, so the shear stress is found to increase linearly with r radial coordinate, radial position. So, that is at center it is 0, and then as you move towards the wall gradually the shear stress increases, and when you reach the wall of the capillary, the shear stress is going to be maximum because r is equals to capital R, that is the maximum value in the radial direction. So, then that value of shear stress would be the maximum, that is known as the wall shear stress, right. Remember, this equation is only for this capillary viscometer. For different geometries you may take slightly different expressions you may get. For this geometry what we see, this tau Rz is directly proportional to the radial position r. Okay. So, till this point what we have done, did we consider anything about the nature of the flow or the nature of the fluid? Nature of the flow in the sense whether it is laminar or turbulent, did we consider? No. Did we consider Newtonian or non-Newtonian? No, we did not consider. Only thing that we consider, the flow has to be fully developed flow, and then it has to be incompressible, steady, incompressible, fully developed flow, that is only we have considered. So, even turbulent flow also it is possible that we may have the fully developed flow conditions, right. So, laminar it's anyway it is possible to have the fully developed flow conditions that we have already seen in transport phenomena courses, right. Whether the fluid, whatever the fluid element that we have taken, we did not say whether it is a Newtonian fluid element or non-Newtonian fluid element. So, that means indirectly this equation whatever develop for the capillary viscometers, whether you take the Newtonian fluid or non-Newtonian fluid, the flow is whether laminar or turbulent, you are going to have this relation valid. So, this equation valid for both laminar and turbulent flow of any incompressible Newtonian or non-Newtonian fluid as long as the flow is fully developed flow, as long as the flow is fully developed flow. And then also it display linear variation of shear stress with the radius. That means shear stress is 0 at the center, because at the center small r is equals to 0. If you substitute a small r is equals to 0 in previous equation, tau rz is equals to minus delta p by L r by 2, you will be getting tau rz is equals to 0, and it is maximum at the tube wall, that is at r is equals to capital R, because capital R is the maximum value possible in this geometry and is known as this, whatever the maximum value of shear stress is known as the wall shear stress. That means tau w is nothing but minus delta p by L capital R by 2. Right. So, in order to have a complete rheological information, the shear stress may be evaluated in terms of the shear rate at the wall, because now we have seen this shear stress. Let us say we take a example, which value of shear stress should we take, that is the problem, right. So, let us say now this is the tube. So, what we have at the wall, it is having tau w maximum value, at the center it is having tau rz is equals to 0 value, right. It is linearly increasing as you move from center to the wall of the tube. Now, should you take tau rz value at this location, at this location, at this location, at this location, or at the wall or at the center? Which one should you take? For that reason only, if you have a very small capillary, let us say if you have a d is equals to 2 mm only. So, that means r is equals to 10 power minus 3 meters. So, if for a constant delta p by L, for a constant pressure gradient, if your diameter of capillary is very small, so then your shear stress, variation in the shear stress from tau rz at r is equals to 0 to tau rz at r is equals to capital R is going to be very small. The difference between these two values is going to be very small. That is the reason we are insisting on using a very narrow gap shearing geometries. That is the reason we are insisting on very narrow gap shearing geometries for measuring the rheology. So, now one thing out of the shear stress versus shear rate, one thing is clear, shear stress information we already got in terms of measurable quantities, like now here in the case of here we are if you know the pressure drop, so then you can easily find out the shear stress, because R, that is the radius of capillary, is known, L, length of the capillary, is also known. So, that means if you know the pressure drop and then dimensions of the capillary, then you can measure the shear stress without any difficulty. So, but now we need to have corresponding shear rate at the wall, that information also we should have. Then your tau w versus gamma dot w information is available, then you can know the rheology of the material. So, for that purpose what we do now, we take the cross section of geometry, capillary whatever is there, we take the cross sectional view now we take. Okay. So, within this one we take one channel or one annulus, right, whose inside diameter is r and then outside diameter is r plus dr, right. Right. So, then if you wanted to know the change in volumetric flow rate dq that is taking place in this considered annulus of inner radius r and then outer radius r plus dr, then you can do dq is equals to 2 pi r vz dr. If you do, you can get the volumetric flow rate information. Consider two fluid elements of radius r and r plus dr. So, the volumetric flow rate through this annulus found by these two fluid elements would be dq is equals to 2 pi r vz dr. Vz is function of r. Now, we are not interested in finding out what is Vz, because for us if you integrate your left hand side, obviously you will get volumetric flow rate for the entire system, that capillary, right. So, that is experimentally but we are not interested in Vz. So, then what we do, we further play with this equation such a way that in the right hand side we get something like minus dVz by dr, which is nothing but gamma dot Rz, which is corresponding to tau Rz. Okay. So, that is what we are going to do. That means indirectly your shear rate may be related to the volumetric flow rate of the fluid passing through the capillary. Okay. So, now this equation when you integrate, you use this integration rule, integral uv is equals to u v1 minus integral u prime v1. So, now that when you apply 2 pi is constant. So, integration of r is r square by 2 and then Vz we are keeping as it is, then minus integration of again integration of r is r square by 2 and then differentiation of Vz is dVz by dr, dVz by dr. So, then what I am doing, I am taking this minus here and then writing plus here, because this minus dVz by dr is nothing but gamma dot Rz, right. So, do not worry about that value substituting gamma dot Rz right now here, we will be doing later on. So, first we will be trying to substitute the limits 0 and then capital R within this expression. So, then what we see, first expression capital R square by 2 and then Vz at R is equals to capital R. R is equals to capital R is nothing but the tube wall. At the tube wall velocity is anyway 0 because of the no slip velocity, and then minus at center R is equals to 0. So, 0 square by 2 Vz. So, that means again this is all this quantity is also 0. So, that means all together whatever this r square by 2 Vz, if you substitute upper and lower limits, so then overall you are going to get 0 anyway, plus this 2 pi multiplied by r square by 2. So, then 2 cancels out. So, then I can have only pi here, integral r square minus dVz by dr r. So, we do not know what is dVz by dr as of now. So, then we cannot substitute this 0 and r values here, and then indeed we do not want it to substitute. So, what you get q is equals to this expression, right. Now, here the nature of flow and characteristics of fluid will be coming into the picture at this point onwards. Okay. At this point onwards, whatever the nature of the flow and characteristics of the fluid comes into the picture, how and those details we are going to see, because if the nature of the fluid is changing, so obviously shear rate is going to change, velocity profile is going to change, so then obviously shear rate is going to change. Okay. So, for laminar flow of time independent fluid, so this is all we are doing for the time independent fluids analysis from this point onwards. The shear rate is determined by the value of the shear stress, something like this, minus dVz by dr is equals to f of tau Rz, f of tau Rz. So, this f function is not known for a unknown fluid. Let us say if you know the fluid shear thinning behavior, so then you have whatever the tau Rz is equals to m gamma dot Rz power n. This is the function. This function is nothing but this one if it is a shear thinning fluid, right. So, but we do not know the nature of the fluid, that is what we are measuring. So, this f is unknown function for a unknown fluid. Okay. Further, what we have seen this tau Rz is equals to minus delta p by L r by 2, equation number 1, and then equation number 2 tau w is equals to minus delta p by L capital R by 2. So, if you divide tau Rz by tau w, then you will be having small r by capital R. So, from here tau w is constant, capital R is constant, tau Rz is varying as R is varying. So, if you differentiate either side, dr is equals to r by tau w d tau Rz you are going to have, because as r changing from 0 to capital R, tau Rz is also changing, though the change is small. In our capillaries cases it is small, but it is there. Okay. So, then you cannot take it as a constant, right. So, now this equation number 6 and 7 we are going to make use in our equation number 5. Equation number 5 is nothing but this volumetric flow rate expression. So, in place of R, you are going to write tau Rz by tau W multiplied by capital R. In place of dr, you are going to write R by capital R by tau W d tau Rz, and then in place of minus dVz by dr, you are going to write f of tau Rz from equation number 6. So, then you have R square tau Rz square divided by tau W square f of tau Rz R by tau W d tau Rz, that is what you are getting. So, now this R cube by tau W cube pi that etc., which are constants, you take to the left hand side. So, that in the next slide you will be having q tau W cube by pi R cube is equals to integral of 0 to tau W tau Rz square f of tau Rz d tau Rz. Okay. So, this is the rearrangement that we have done. After doing the integration, whatever, if you know the, let us assume if you know that f of tau Rz function, so then if you do the integration and then substitute the limits, so then you will be getting the value in terms of tau W only, irrespective of the fluid, whichever fluid it is. Okay. So, that is RHS of above equation embodies a definite integral, thus irrespective of nature of f of tau Rz. That means irrespective of nature of f of tau Rz in the sense irrespective of the nature of the fluid, whether it is shear thinning, shear thickening or viscoplastic, the final results is going to depend only on tau W, obviously, because the limits are 0 and tau W are the two limits, lower and upper limits for this integration. So, now what we do, this equation number 9 we are going to differentiate with respect to tau W. So, now left hand side you have to see the tau W is there. So, then that differentiation you can easily do, but q whatever is there, can you take it independent of tau W? No, you cannot, because it is q is related to the shear rate or velocity change in is related to the velocity gradient, and then velocity gradient is related to the shear stress. So, then obviously wall shear stress is going to be affected because of this k wall. I mean they are interrelated, so then that should be taken care appropriately. So, d by d tau W of q tau W cube by pi R cube is equals to d by d tau W of integration 0 to tau W tau Rz square f of tau Rz d tau Rz. This is what we are having. So, now this equation, what you understand, right hand side, it is having Leibniz form. It is having Leibniz form, that is d by ds prime of integral 0 to s prime s square f of s ds is equals to s prime f of s prime. That is what you have. So, now here in this case s prime is nothing but tau W, s is nothing but tau Rz. So, the right hand side whatever is there, if you apply the Leibniz rule, so you will be getting tau W square f of tau W you are going to get. So, right hand side tau W square f of tau W you are getting, left hand side we are not doing the differentiation as of now, we will be doing subsequently. Right. So, now we will be doing the differentiation of the left hand side also. When you do it, you will get 3 tau W square q by pi R cube plus tau W cube by pi R cube d cube by d tau W, but this pi R cube I am keeping within the differentiation because of some reason, subsequently we are going to realize it, right. So, now f of tau W, if you keep one side, rest other terms you take to the other side. So, then what you have, 3 q by pi R cube plus tau W d by d tau W of q by pi R cube. So, now this equation what we are going to do, in the right hand side both the terms we are multiplying and then dividing by 4, and then for the second term we are using this dln of x is nothing but dx by x form. So, that we can write 4 cube by pi R cube multiplied by 3 by 4 as a first term in the RHS. Second term in the RHS we can write it as 1 by 4 dln 4 cube by pi R cube divided by dln tau W multiplied by 4 cube by pi R cube. So, then what we are having, we can cross check, let us say we have a 1 by 4 here whether are we getting the same term or not. So that should be d ln x is dx by x. So d of 4 cube by pi r cube divided by 4 cube by pi r cube, and then d ln tau w we can write d tau w by tau w. So another 4 cube by pi r cube is as it is here. So then this 4 cube by pi r cube, this 4 cube by pi r cube is cancelled out, so that within the this whatever the within this differentiation 4 is there, that this 4 can be cancelled out. So then we can have tau w d by d tau w of q by pi r cube. So that is nothing but this entire term is nothing but whatever the second term in the RHS. In the subsequent step, what we are doing, we are taking 4 cube by pi r cube as a common term, right. Then we have 3 by 4 plus 1 by 4 d ln 4 q by pi r cube divided by d ln tau w. So this is the equation. Once again we have written like this here. Okay. So now what you understand here, if you apply in terms of average velocity, right, whatever the q in this above equation, if you replace by average velocity terms, then q by pi r square, q by pi capital R square is nothing but average velocity of the fluid that is flowing through the capillary for a given delta p. So that average velocity let us take as a v, and then in place of r, what you can write? You can write d by 2. Then you have this equation. Let us say we will do this one only. 4 in place of q we can write v pi r square divided by pi r cube we are having. So 4 v pi is cancelled out, square of here and then cube of here is gone. So then r we are having. So then further r, if you write d by 2, then 8 v by d we are having. So 8 v by d here, 3 by 4 plus 1 by 4 d, again here also 8 v by d divided by d ln tau w. This is what we are having. Now this is what this f of tau w is nothing but, this is nothing but we have seen already, f of tau r z is nothing but minus dvz by dr. So f of tau w should be nothing but minus dvz by dr at r is equals to capital R. So that is nothing but this one. In place of f of tau w, I am writing minus dvz by dr at r is equals to capital R. So that means this whatever the gamma dot rz at wall or gamma dot wall information is there, that you already got it here, But the problem is that what is we have to analyze subsequently, and then what about this term, what about this term and all that. So for the analysis, what we do, we take a known fluid flowing through the capillary. The known fluid is nothing but Newtonian fluid. If Newtonian fluid is flowing through a infinitely long circular pipe, then what we know, pressure drop expression, we can get for that case by Hagen-Poiseuille equation, that we know. So that Hagen-Poiseuille equation is nothing but minus delta p by L is equals to 32 mu v by d square. Remember, this is for the Newtonian fluid only. There is a point for writing this one, we will be realizing next step. So now what I am doing, I am keeping v only in the right hand side, rest of all the terms I am taking to the left hand side. Also I am converting the d in terms of r. It is not required anyway, but for some reasons. So then further left hand side, what I am doing, minus delta p by L r by 2 I am writing as one term, and then remaining r by 4 mu as the other term. So this r by 4 mu I take it to the right hand side and then join with v, so that I can have right hand side 4 mu v by r and then left hand side minus delta p by L r by 2. this now what we do, whatever this r is there, again we will be writing d by 2, so that we can have 8 v by d mu in the right hand side, left hand side minus delta p by L r by 2 is there. So, which is nothing but tau w, minus delta p by L capital R by 2 is nothing but tau w, which is true irrespective of the nature of the fluid, whether it is Newtonian or non-Newtonian for this geometry, for this flow geometry. Right hand side 8 v by d mu we are having. So, now what is the relation for the Newtonian fluid? Tau is equals to mu gamma dot, isn't it? So, that means from here what we understand by applying the Newton's law of viscosity here, and then analogously if you see, this 8 v by d is nothing but gamma dot w, isn't it? W because we are measuring at the wall, and then geometry we have taken that variations are very small as we move from a center to the wall. Okay. So now 8 v by d is true shear rate at the wall for Newtonian fluid. In the previous equation 13 we are going to see what we are having, that minus dvz by dr at capital R is nothing but 8 v by d multiplied by 3 by 4 plus 1 by 4 d ln 4 cube by pi r cube divided by d ln tau w, that is what we have seen, right. So, in this equation whatever this additional term is there, it should be a kind of a correction for the 8 v by d value, which is true for the Newtonian case only. For Newtonian case 8 v by d is shear rate, true shear rate, right. Remember all this analysis we are doing for time independent non-Newtonian fluids only, and then time independent non-Newtonian fluids are also known as the generalized Newtonian fluids. So, that is the reason we are making connection with the Newtonian case here, right. So, now for the Newtonian case 8 v by d is the true shear rate, but it is not true shear rate for the non-Newtonian fluid. So, then there is a correction. If this correction whatever available in the within the this parenthesis 3 by 4 plus 1 by 4 d ln 8 v by d divided by d ln tau w, if it is close to 1 or equals to 1, directly we can say this fluid is a Newtonian fluid, unknown fluid is a Newtonian fluid. If it is not equals to 1, so then we cannot say that the material is a Newtonian fluid. So, that means for non-Newtonian fluids, for time independent non-Newtonian fluids, this 8 v by d is often regarded as apparent shear rate or nominal shear rate. Okay. So, we have to make this correction. So, now further what we do, whatever d ln tau w by d ln 8 v by d is there, that we take it as n prime, which is nothing but the slope of tau w versus 8 v by d plot on a log-log graph sheet. On a log-log graph sheet, if you plot tau w versus 8 v by d whatever is there, so whatever the slope is there, that slope we are taking n prime. So, that equation number 13 we can write in place of this, we can write 1 by n prime. So, that we have 3 n prime plus 1 by 4 n prime multiplied by 8 v by d is nothing but minus dvz by dr at wall, which is nothing but gamma dot w. So, for time independent non-Newtonian fluids, tau w is equals to minus delta p by L capital R by 2, and then shear rate gamma dot w is nothing but 8 v by d multiplied by 3 n prime plus 1 by 4 n prime. If n prime is close to 1, then it is a Newtonian fluid, because this correction factor is 1, we will be having only 8 v by d. So, what we understand, if you have the pressure drop and then average velocity from your capillary rheometer experiments, right. So, you can change pressure drop and then get the different volumetric flow rate. So, then Q versus delta P information you can get enough number of experiment you do, and then Q you convert in terms of V average or V, as we are using the symbol V here. So, then corresponding tau w and then gamma dot w you can get from these equations, and then when you plot them, if you get a straight line passing through the origin. So, then you can say that material is a Newtonian fluid, otherwise it is not a Newtonian fluid, that is what you can understand. So, where n prime here vary with the nominal shear rate for non-Newtonian fluids. So, in the next lecture what we will be discussing? We will be discussing different modes of operating capillary viscometers, and then we see a few example problems, and then we see sources of errors. We are saying that narrow gap, if you take the variation in the shear rate or shear stress as you move from the center of the capillary to the wall of the capillary is small, but sometimes it may not possible. So, then there may be variation. So, if there are inconsistencies, how to incorporate? Inconsistency in the sense you use different capillaries of different length and diameter, and then do the experiment, and then you whatever the Q versus delta P information that you get for different capillaries of different length and diameter, you convert them in terms of tau versus gamma dot information. Whatever the Q versus delta P information is there, you convert them in terms of tau versus gamma dot, and then you plot. If all of them are not superimposing onto each other, that means there is inconsistency. Inconsistency may be because of some possible source of errors. So, what are those sources of errors? If the sources of errors are there, we should able to make appropriate corrections. Those things we are going to see in the next lecture. So, the references for this lecture are given here. Majority of details have been taken from this book for this lecture. Okay. But however, similar analysis you may also find in other books provided here. Thank you.